Astronomers have uncovered a cosmic mystery unlike any other. Nearly every nearby galaxy, including our Milky Way, is moving toward a specific region of space for reasons we don't fully understand. Instead of drifting apart with the universe's expansion, galaxies appear to be flowing towards something immense and unseen, hidden deep behind the Milky Way's dense plane. This powerful gravitational pull, known as the Great Attractor, has puzzled scientists for decades. What could be so massive, so influential, yet so invisible that it moves entire galaxies across millions of light years? So, if you want to uncover the full story behind this cosmic enigma, make sure to watch this video till the end and subscribe to the channel. Let's begin. Under normal circumstances, galaxies move apart from one another because of the universe's continual expansion, a motion first observed by Edwin Hubble nearly a century ago. This expansion stretches space itself, causing distant galaxies to recede from us at speeds proportional to their distance. The farther away a galaxy is, the faster it appears to be moving away. It's a beautifully simple relationship, and for decades, it seemed to describe the large-scale structure of the cosmos perfectly. But then, something strange emerged from the data. When astronomers began mapping the motions of nearby galaxies, they noticed a curious deviation from this cosmic pattern. The galaxies weren't just being carried along by the expansion of space. They were also drifting in a particular direction, as if being pulled by some massive, invisible force. It wasn't random turbulence or local gravitational effects. It was a coherent flow involving thousands of galaxies, all moving toward the same hidden point in the sky. This wasn't supposed to happen. According to our understanding of cosmic expansion, galaxies should recede uniformly, except for small motions caused by local gravity. Yet here was a large-scale, coordinated motion spanning hundreds of millions of light-years. Galaxies not only expanding with the universe, but sliding sideways through it, drawn towards something incredibly powerful and completely unseen. This discovery hinted at a deeper structure of the cosmos, one shaped by enormous gravitational forces lurking in regions still beyond our full view. And that led astronomers to ask, what could possibly cause such an immense flow across the heavens? This immense, invisible force tugging on entire galaxies eventually earned a name: the Great Attractor. The term might sound like it refers to a single, colossal object, like some kind of supermassive black hole or a gargantuan cluster hidden in the dark. But in truth, the Great Attractor isn't a single object at all. It's a vast region of space, hundreds of millions of light years across, where gravity appears to be unusually strong, enough to alter the motion of galaxies on an enormous scale. Scientists coined the name in the late 20th century to describe this mysterious gravitational anomaly, a kind of cosmic basin in which galaxies seem to flow as if drawn by an unseen current. Rather than being one central point, it's more like a gravitational landscape, a region dense with matter, both visible and invisible, warping the surrounding space-time and guiding galaxies toward it. What makes it so fascinating is that we can't directly observe what's causing this gravitational pull. The visible galaxies in that area simply don't contain enough mass to explain the strength of the attraction. This means the Great Attractor could be composed of an enormous concentration of hidden mass, dark matter, galaxy clusters, and superclusters, all buried behind a thick curtain of cosmic dust and gas. Its pull is so powerful that even our Milky Way, moving at hundreds of kilometers per second, is caught in its grip. The Great Attractor stands as a gravitational mystery on a cosmic scale, a reminder that the universe still holds vast, unseen structures shaping the very motion of galaxies themselves. The story of the Great Attractor's discovery begins in the 1970s, a time when astronomers were starting to map the large-scale motion of galaxies with greater precision than ever before. Until then, the universe had been viewed largely as an orderly, expanding system where every galaxy moved away from every other according to Hubble's law. But as observational technology improved, scientists began noticing subtle deviations in the motion of galaxies near our own cosmic neighborhood. These weren't just small wobbles or random drifts. Entire clusters of galaxies seemed to be veering off course, moving not only outward with the cosmic expansion, but also sideways, as though pulled by a hidden gravitational hand. This realization didn't happen overnight. It was the result of years of painstaking measurements and analyses. Astronomers studied redshifts, the stretching of light from galaxies moving away due to the expansion of the universe, and found that these redshifts weren't perfectly uniform. Some galaxies appeared to be moving faster than expected, while others lagged behind. When these differences were mapped across the sky, a startling pattern emerged. Galaxies in our local region, including the Milky Way, were all drifting toward a particular direction in space. By the early 1980s, this mysterious direction had been pinpointed to an area near the constellations Centaurus and Hydra, roughly 250 million light-years away. The data suggested that something massive lurked there, warping the motion of thousands of galaxies across hundreds of millions of light-years. It wasn't just the Milky Way. The entire local group of galaxies, along with neighboring galaxy clusters like Virgo, appeared to be moving toward this enigmatic point. Astronomers called this motion the peculiar velocity, a movement not accounted for by universal expansion, but by gravity itself. At first, the evidence was puzzling and controversial. Could such a large-scale motion really exist? After all, the universe was supposed to be homogeneous on the grandest scales, smooth and uniform, with no single direction or location exerting such dominance. But as more and more data poured in, the trend became undeniable. The galaxies weren't merely expanding apart, they were flowing like cosmic rivers toward a hidden center of mass. This realization hinted that the universe might be structured in a far more complex way than previously imagined, with enormous concentrations of mass creating gravitational basins that shape the motion of galaxies over unimaginable distances. The discovery of this cosmic flow was one of the most profound findings of its time. It challenged long-held assumptions and sparked intense debate among cosmologists. Some speculated that the cause might be a gigantic supercluster of galaxies lying in that direction. Others suspected that it could be a vast, unseen mass of dark matter, an invisible gravitational force dominating that region of space. But the problem was clear. This part of the sky was exceptionally difficult to study. The area toward which all these galaxies were moving was located in a section of the heavens heavily obscured by our own galaxy's dense disk. Dust, gas, and countless stars blocked much of the visible light coming from that region, making it nearly impossible to see what lay beyond. Still, through indirect measurements, astronomers were able to confirm that our entire galactic neighborhood, including the Milky Way, the Virgo cluster, and even more distant galaxies, was being drawn toward this hidden point with a velocity of hundreds of kilometers per second. The Great Attractor, as it would later be called, was not just an astronomical curiosity. It was a revelation. It meant that the universe was far from uniform on these scales, that immense gravitational structures, invisible yet incredibly influential, could shape the motion of entire swaths of the cosmos. And though the exact source of this gravitational pull remained concealed, its effects could be felt across an astonishing volume of space. By the end of the 1980s, it was clear that the Great Attractor was real. Galaxies were not merely expanding uniformly into the void. They were drifting together towards something massive and mysterious near the Centaurus constellation. It was as though a cosmic tide was flowing across the universe, carrying galaxies along with it. A gravitational current pointing us toward a hidden realm behind the dense plane of the Milky Way. This discovery would set the stage for decades of further research, driving astronomers to peer deeper into the obscured regions of our sky in search of the cause. What was behind that gravitational curtain? What kind of structure could bend the motion of entire galaxy clusters? And if the Great Attractor could influence our galaxy's motion, how many other unseen forces might be shaping the broader universe? The realization that our own Milky Way is not stationary, but caught in this grand cosmic drift, forever changed our perception of our place in the cosmos. We are not simply orbiting our galactic center or expanding outward with the universe. We are moving through space as part of a much larger flow, drawn toward a destination we cannot yet see. That motion toward the Great Attractor has become one of the most intriguing clues to the hidden architecture of the universe, a puzzle that continues to challenge and inspire astronomers to this day. When astronomers finally realized that thousands of galaxies, including our own Milky Way, were streaming toward a specific part of the sky, their first instinct was to look closer, to see what was there. But when telescopes turned toward that mysterious direction near the constellations Centaurus and Hydra, they encountered an immediate and frustrating obstacle. The region was cloaked behind one of the densest and most obstructive parts of the Milky Way's disk, a cosmic curtain of dust, gas, and stars that obscures our view of the universe beyond. This barrier made direct observation nearly impossible, creating one of the most significant challenges in extragalactic astronomy: the problem of visibility. To understand why this is such a formidable issue, it helps to consider what our galaxy looks like from within. The Milky Way is a vast, spiral-shaped system of hundreds of billions of stars. From our vantage point on Earth, we are embedded within one of its spiral arms, looking outward through layer upon layer of interstellar material. When we gaze toward the galactic center, or along the plane of the disk, our line of sight cuts through dense clouds of gas and dust that absorb and scatter visible light. These clouds act like a fog, not only dimming the light from distant stars and galaxies, but completely blocking it in some directions. This means that certain regions of the sky are effectively hidden from view in optical wavelengths, invisible to ordinary telescopes. And, as fate would have it, the very region where the Great Attractor resides lies deep within this obscured zone. It's not just a little inconvenient, it's one of the most light-blocked areas of the entire sky. Astronomers found themselves staring into what looked like a black wall of cosmic fog, knowing that something immensely powerful lay just beyond it, pulling entire galaxies toward its hidden core. The problem isn't that the Great Attractor is too far away. It's roughly 150 to 250 million light-years from Earth, which is relatively close in cosmic terms. The issue is that the Milky Way's disk, which dominates our sky, blocks more than 20% of the observable universe in visible light. This blocked region forms a band across the sky, where dust and stars outshine or obscure everything behind them. For astronomers trying to map cosmic flows and galaxy distributions, this presents a serious blind spot, one that hides not just individual galaxies, but possibly massive clusters and superclusters of galaxies that could explain the gravitational pull we detect. To visualize this, imagine standing in a dense forest at night with a flashlight. You can see the trees right in front of you, but beyond them, the beam of light scatters and fades in the thick fog. You might sense that there's something beyond the mist, perhaps a mountain or a valley, but you can't see it directly. That's the situation astronomers face when they look toward the Great Attractor in visible light. The dense fog of interstellar dust blocks almost all optical wavelengths, leaving only hints of the structures that lie beyond. This obscured zone became known as the Zone of Avoidance, a poetic yet frustrating name for the region where the Milky Way's brightness and opacity prevent us from seeing what's behind it. For many years, this zone made it nearly impossible to study the Great Attractor directly. Scientists could only infer its presence through indirect means, by measuring how galaxies outside the zone were moving, and by detecting subtle distortions in their velocities that pointed toward the hidden mass. It was like trying to locate a ship in a foggy ocean by watching how the surrounding waves move. Even though visible light telescopes couldn't penetrate the thick curtain of dust, astronomers didn't give up. They began exploring alternative wavelengths of light, such as radio, infrared, and X-ray, which can pass through interstellar dust far more effectively than visible light. Infrared observations, for example, can detect the faint glow of stars that lie behind the Milky Way's veil, while radio telescopes can pick up emissions from hydrogen gas in galaxies beyond the obscured zone. These new tools allowed scientists to start mapping what was once hidden, slowly revealing the structures that might contribute to the Great Attractor's pull. But even with these advances, the problem of visibility remains daunting. The Milky Way's dense plane is not just filled with gas and dust. It's also crowded with millions of bright stars whose light overwhelms faint background sources. Distinguishing between a dim, distant galaxy and a nearby star requires careful analysis, and even then, many galaxies are simply too obscured to detect. It's as though the universe placed its greatest gravitational mystery directly behind the brightest and most opaque part of our own galaxy, as if daring us to uncover it. This invisible barrier has, in a sense, preserved the mystery of the Great Attractor. We know it's there. We can feel its gravitational influence through the motions of galaxies, but we can't see it directly. The problem of visibility has forced astronomers to become detectives of cosmic motion, piecing together evidence from velocity maps, non-visible wavelengths, and computer simulations to reconstruct the hidden structures behind the Milky Way. The irony is profound. The Great Attractor, one of the most massive and influential regions in our cosmic neighborhood, is concealed right behind our own galactic curtain. It's a humbling reminder that, despite all our telescopes and technologies, our view of the universe is still limited, shaped as much by what we can't see as by what we can. And as we stare into that luminous fog, we're left with the haunting certainty that behind it lies something vast, ancient, and immensely powerful, continuing to pull our galaxy and countless others toward its unseen heart. Astronomers, in their quest to unravel the mystery behind the strange motion of galaxies, soon came to a realization. The very region toward which all these galaxies seem to be moving was buried within what they came to call the zone of avoidance. The name itself sounds like something from a science fiction story, a forbidden region, a place beyond reach. Yet in this case, it's an entirely real and deeply frustrating obstacle in observational astronomy. The zone of avoidance refers to the broad band of sky obscured by our own Milky Way's disk, a region so densely packed with stars, dust, and gas that it effectively hides whatever lies beyond. From Earth, the Milky Way stretches across the night sky as a bright, milky band of light, a stunning view that ancient civilizations romanticized as the river of heaven. But for astronomers, this beautiful sight conceals a tremendous challenge. The light we see from the Milky Way comes from billions of stars and dense molecular clouds concentrated along the galactic plane. When we point our telescopes in that direction, visible light from distant galaxies simply cannot penetrate the thickness of this material. Dust particles within the interstellar medium absorb and scatter starlight, blocking much of what lies behind. The result is an optical blind spot that covers roughly 10 to 20% of the entire sky. The zone of avoidance isn't empty, far from it. It's filled with countless stars, star-forming regions, and nebulae within our own galaxy. But that brightness is precisely the problem. It overwhelms the faint light from distant galaxies far beyond. Imagine trying to spot a candle flame on the horizon while standing under the midday sun. That's what it's like to search for galaxies behind the Milky Way's disk. And as fate would have it, the Great Attractor lies right in the heart of this hidden zone. This fact turned what could have been a straightforward astronomical investigation into a decades-long challenge. When astronomers first identified the peculiar motions of galaxies, suggesting a massive gravitational source, they immediately tried to map what lay in that direction. Yet, when they looked toward the coordinates, near the constellations Centaurus and Norma, they were met not with a deep, clear view of distant galaxies, but with a luminous fog of starlight and an almost impenetrable wall of dust. It was as if the universe had deliberately hidden one of its greatest secrets behind our own cosmic backyard. The zone of avoidance became notorious among astronomers. For many years, it was treated as a kind of no-go area, a region avoided in galaxy surveys simply because it was so difficult to observe. The name, zone of avoidance, was first coined in the mid-20th century when astronomers noticed that their maps of galaxies had a peculiar empty band running across them. This wasn't because there were no galaxies there, but because telescopes couldn't detect them through the Milky Way's veil. It appeared as though galaxies simply avoided that region, hence the name. But science, driven by curiosity and determination, eventually refused to accept that this zone should remain unexplored. In the latter half of the 20th century, as technology advanced, astronomers began to develop new strategies to peer through the darkness. Infrared astronomy became a game changer. Unlike visible light, infrared radiation can pass through interstellar dust far more effectively, revealing the faint glow of galaxies previously hidden from sight. Radio astronomy also opened a new window into this obscured region, since radio waves can travel through gas and dust without significant interference. Using these tools, astronomers began to uncover what lay within the zone of avoidance, and what they found was astonishing. Hidden behind the Milky Way's thick disk was not an empty void, but a vast and complex network of galaxies, clusters, and superclusters, immense cosmic structures that had simply been invisible to us for centuries. Among them lay the suspected location of the Great Attractor, buried deep within the densest part of the zone. This discovery transformed the way scientists viewed our cosmic neighborhood. It meant that our understanding of galaxy distribution, cosmic flows, and gravitational structures had been incomplete for decades, not because of a lack of effort, but because of a literal wall of galactic material standing in the way. The zone of avoidance wasn't merely an observational inconvenience. It was the key to understanding one of the most significant gravitational anomalies in our local universe. To map it properly, astronomers began large-scale efforts to survey the galaxies behind the Milky Way using multi-wavelength observations. These surveys revealed the outlines of massive galaxy clusters and filamentary structures stretching across space, cosmic highways of matter leading toward the heart of the Great Attractor. Yet even with modern technology, parts of this region remain frustratingly difficult to observe. The Milky Way's core and its thick dust lanes continue to obscure certain wavelengths, leaving gaps in our understanding of exactly what resides there. What's perhaps most haunting is the realization that we can feel the Great Attractor's gravitational influence, even if we can't directly see its source. Our Milky Way, along with thousands of other galaxies, is moving toward it at remarkable speeds, hundreds of kilometers per second, but we still can't visualize the full structure responsible for that pull. It's as if the universe is whispering to us through gravitational clues, hinting at the existence of something vast and powerful hidden just beyond the curtain. The zone of avoidance remains one of the most fascinating and challenging regions in modern astronomy, not because it's an empty void, but precisely because it's so full of both mystery and matter. Behind that glowing, star-filled belt that decorates our night sky lies a gravitational enigma that continues to shape the movement of galaxies across the cosmos. The Great Attractor, concealed within this hidden zone, serves as a reminder that even in an age of space telescopes and deep cosmic surveys, the universe still holds secrets just beyond the reach of our sight, waiting patiently to be revealed. If astronomers can't directly see the Great Attractor, then how do they know it's there? The answer lies in the subtle language of light itself, specifically in how the light from distant galaxies shifts depending on their motion through space. This phenomenon, known as redshift and blueshift, is one of the most powerful tools in the astronomer's toolkit. It allows scientists to measure how fast galaxies are moving and in what direction, not by watching them change position, which would take millions of years, but by studying the color of the light they emit. To understand this, imagine the familiar sound of a passing siren. As an ambulance approaches, its sound waves are compressed and the pitch you hear rises. As it moves away, those waves stretch out and the pitch drops. This is the Doppler effect, and it doesn't just apply to sound, it applies to all kinds of waves, including light. When a galaxy moves away from us, the light waves it emits are stretched, causing them to shift toward the red end of the spectrum. This is called redshift. Conversely, when a galaxy moves toward us, its light waves are compressed, shifting toward the blue end of the spectrum, a blueshift. By measuring the amount of redshift or blueshift in a galaxy's light, astronomers can determine its velocity relative to Earth. This is how we know that, on a large scale, galaxies are moving away from each other as the universe expands. Their light is redshifted in proportion to their distance, a relationship first discovered by Edwin Hubble in 1929. But when astronomers began mapping these redshifts in detail, they noticed peculiar deviations from what Hubble's law predicted. Some galaxies weren't just receding due to cosmic expansion. They had an extra velocity component, a peculiar motion, indicating they were being gravitationally pulled in a specific direction. This was the first major clue that something unseen was influencing their movement. Astronomers meticulously gathered data from hundreds, then thousands of galaxies, using optical and radio telescopes to measure their redshifts. When they plotted these motions in three-dimensional maps, a strange pattern appeared. Galaxies on one side of the sky seemed to be moving slightly faster in one direction than expected, while those on the opposite side showed motion suggesting a pull in the same direction. It was as though space itself was flowing toward a single point, the mysterious gravitational well we now call the Great Attractor. The evidence became even more compelling when scientists studied the cosmic microwave background, CMB, the faint afterglow of the Big Bang that fills the universe. The CMB provides a kind of cosmic rest frame, allowing astronomers to measure how the Milky Way itself is moving relative to the background radiation. What they found was stunning. Our entire galaxy, along with its local group of neighboring galaxies, is moving at roughly 600 kilometers per second toward a point in the sky that aligns remarkably well with the direction of the Great Attractor. This motion, known as the CMB dipole anisotropy, is one of the clearest indicators that we are being drawn toward a region of enhanced gravitational pull. It's not just the Milky Way. The entire Virgo Supercluster, the larger structure that contains our galaxy and thousands of others, shares this same motion. The data shows a coherent flow of galaxies, like water streaming down a cosmic slope, all heading toward the same gravitational basin. To make these measurements, astronomers rely on highly sensitive instruments that can detect and analyze spectral lines, the distinct fingerprints of chemical elements in a galaxy's light. These lines shift depending on the galaxy's motion. Even a small change in wavelength can reveal motion of hundreds of kilometers per second. Observatories like the Parkes Radio Telescope in Australia, the Arecibo Observatory, before its collapse, and later infrared and microwave telescopes like those aboard the Planck satellite, have all contributed to refining these measurements with incredible precision. But it's not as simple as measuring a single redshift value. Astronomers must carefully separate the effects of the universe's general expansion from local gravitational motions. Every galaxy has both a velocity due to cosmic expansion and an additional motion due to the gravitational pull of nearby structures, galaxy clusters, filaments, and, of course, massive attractors like the one hidden in the zone of avoidance. By subtracting the expansion component, scientists can isolate the peculiar motion, the velocity that points toward whatever is causing the gravitational attraction. When these peculiar velocities are mapped across vast regions of space, a clear pattern emerges. Galaxies are flowing along enormous cosmic filaments, highways of matter that weave through the universe, and converging toward dense regions of mass. One of these convergence points lies squarely in the direction of the Great Attractor. Even though we cannot see it directly through visible light, we can measure its influence through these motions. The gravity there is strong enough to distort the trajectories of entire galaxy clusters over hundreds of millions of light years. It's a humbling realization. We can't see the Great Attractor, but we can feel its presence in the way the universe moves around it. Its gravitational signature is written in the red and blue shifts of distant galaxies, the faint but unmistakable fingerprints of an unseen giant. Through these delicate shifts in light, the cosmos itself reveals the invisible structures that shape it. In a sense, the redshift and blueshift measurements act like a cosmic sonar system. We send no signal, but the universe sends one to us, encoded in every photon that reaches our telescopes. Each tiny shift in wavelength tells a story of motion, of attraction, of the grand cosmic choreography that binds galaxies together in an intricate gravitational dance. And as we continue to refine our instruments and deepen our observations, that story becomes ever clearer. Somewhere beyond the Milky Way's veil, an enormous mass concentration, the Great Attractor, exerts its silent, irresistible pull on our entire galactic neighborhood. The scale of the Great Attractor's influence is almost beyond comprehension. To truly appreciate it, we need to translate those subtle shifts in light and those cosmic flows into tangible numbers, figures that capture just how powerful this hidden force really is. Every galaxy in our cosmic neighborhood, including the Milky Way, is not stationary in space. Instead, it's racing through the void, drawn relentlessly towards something we cannot see, at staggering speeds. Astronomers have measured that our entire local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, is hurtling toward the direction of the Great Attractor at approximately 600 kilometers per second. That's more than 2 million kilometers per hour, or nearly 1.3 million miles per hour. To put that into perspective, at this speed, our entire galaxy, a disk of stars 100,000 light-years wide, moves a distance equal to the diameter of Earth every single second. And yet, despite that blistering velocity, the pull is so immense and spread across such vast cosmic distances that we will never arrive at the Great Attractor in any humanly imaginable time frame. The journey would take hundreds of millions of years, and by then, the cosmic landscape itself will have evolved into something entirely different. But the sheer velocity tells us something extraordinary. Whatever lies in that hidden region must possess an almost unimaginable gravitational mass. Gravity, after all, weakens with distance. For a force located 150 to 250 million light-years away to affect not just a few nearby galaxies, but entire clusters, even whole superclusters, it must be anchored in an enormous concentration of matter. Astronomers estimate that the mass influencing this flow could be equivalent to tens of thousands of Milky Way-sized galaxies, concentrated in a relatively compact volume of space. our Milky Way is not alone in feeling this gravitational tug. Observations show that nearby galaxy clusters, such as the Virgo cluster and the Hydra Centaurus supercluster, are also moving in the same general direction. Even more distant galaxies beyond our local cosmic neighborhood exhibit motion consistent with this pull. The influence extends across a region hundreds of millions of light-years wide, a gravitational reach so vast that it reshapes the motion of entire cosmic structures. It's as though the Great Attractor sits in a deep gravitational basin, and galaxies all around it are slowly sliding inward, like water funneling toward the lowest point in a vast cosmic landscape. This flow is not chaotic, it's coherent, meaning galaxies separated by millions of light-years are moving in the same general direction at similar speeds. Such coordinated motion implies that the cause is not local or isolated, but rather the result of a massive, large-scale distribution of matter. The velocities themselves, hundreds of kilometers per second, might seem like small ripples compared to the overall expansion of the universe, but they represent powerful local distortions in the cosmic fabric. It's important to understand how this movement fits within the broader dynamics of the universe. The universe is still expanding, driven by dark energy, and galaxies are generally moving away from one another as space itself stretches. Yet, superimposed on this global expansion are local gravitational effects, regions where matter is dense enough to resist the pull of cosmic expansion. The Great Attractor represents one of these regions. Even though the universe is expanding, the gravitational mass concentrated there bends space-time so strongly that galaxies within its influence deviate from the smooth expansion flow, turning inward toward this hidden gravitational center. The Milky Way's peculiar velocity, the motion not explained by cosmic expansion, is about 370 kilometers per second relative to the cosmic microwave background, with additional components bringing our total velocity toward the Great Attractor to around 600 kilometers per second. The Virgo cluster, a massive structure about 50 million light-years away, is moving in roughly the same direction, though at a slightly different speed. When you map the flow of galaxies in 3 dimensions, they all seem to be converging toward a gravitational basin near the constellations Centaurus and Norma. The incredible part is that even with such enormous velocities, we are still only subtly influenced by this cosmic motion in our daily perspective. From Earth, the stars seem fixed, their relative motions imperceptible to the naked eye. Yet the truth is that our entire galaxy, containing hundreds of billions of stars, is collectively moving, not just rotating around its own center or orbiting within the local group, but sliding through intergalactic space towards something so massive and mysterious that it bends the motion of the universe itself in our vicinity. The intensity of the Great Attractor's gravitational pull cannot be overstated. It is estimated to have a mass equivalent to hundreds of quadrillions of suns, far exceeding anything found in our immediate cosmic environment. Its influence extends well beyond what gravity from ordinary visible matter could produce, which is one of the main reasons astronomers suspect that a huge portion of its mass comes from dark matter, the invisible substance that makes up roughly 85% of all matter in the universe. If we could visualize this gravitational landscape, we would see the universe as a kind of cosmic topography, with galaxies moving not in random directions, but flowing like rivers down invisible valleys carved into the fabric of space-time by massive concentrations of matter. The Great Attractor would appear as one of the deepest of these valleys, an immense gravitational sinkhole that redirects the flow of entire galaxy clusters toward it. And yet, for all its might, the Great Attractor is not the final word in cosmic gravity. It's part of an even larger system of attraction that stretches far beyond it, a clue that the cosmic web is interconnected by vast chains of matter, each influencing the motion of the next. But before astronomers could uncover that grander structure, they had to look more closely at what lay hidden in the direction of the Great Attractor itself. That investigation would lead to the discovery of an even more tangible component of this gravitational mystery, a colossal galaxy cluster buried behind the Milky Way's veil, known as the Norma cluster. When astronomers first detected the strange, large-scale motion of galaxies toward a specific region of the sky, they were both thrilled and perplexed. The data was unmistakable. Entire clusters, superclusters, and even our Milky Way were being drawn toward a massive gravitational source located in the direction of the constellations Centaurus and Hydra. But when they looked there, they saw almost nothing. The light from that region was dim, scattered, and blocked by the Milky Way's thick band of dust and stars. So began one of the great astronomical mysteries of the 20th century. What exactly is the Great Attractor? The first hypotheses arose in the late 1970s and early 1980s, when astronomers such as Alan Dressler, Donald Lynden Bell, and others began to interpret peculiar velocity data, measurements of galaxy motions that deviated from the expected uniform expansion of the universe. They noticed that these peculiar velocities were not random. Instead, they pointed consistently toward a specific point in space roughly 200 to 250 million light-years away. This led to the revolutionary idea that there must be an enormous mass concentration hidden in that direction, exerting a gravitational influence over vast regions of the cosmos. In those early days, the nature of the Great Attractor was a matter of intense debate. One of the most straightforward ideas was that it might be a gigantic cluster of galaxies, perhaps even larger than any known cluster at the time. After all, galaxy clusters are the most massive gravitationally bound structures in the universe, containing thousands of galaxies bound together by gravity. If such a cluster existed in the zone of avoidance, it could easily produce the kind of large-scale motion astronomers were observing. However, when astronomers tried to detect such a structure in visible light, they found little to support the theory. There were no obvious concentrations of galaxies in that direction that could account for the gravitational pull. The optical surveys revealed only a faint scattering of galaxies, far too few to explain the magnitude of the observed motion. This only deepened the mystery. If the gravitational source wasn't visible, then what was it? That's when more speculative hypotheses began to emerge. Some scientists proposed that the Great Attractor might be composed largely of unseen matter, material that doesn't emit or reflect light, but which nonetheless exerts gravitational force. This idea, though still controversial at the time, was part of a growing awareness of the existence of dark matter, an invisible substance inferred from the rotation of galaxies and the motion of galaxy clusters. The thought was tantalizing. Perhaps the Great Attractor was a vast concentration of dark matter, dense enough to warp the motion of nearby galaxies, yet invisible through any optical telescope. Others entertained even bolder ideas. Some speculated that the Great Attractor might represent a unique type of cosmic structure, perhaps an enormous wall or filament in the large-scale web of the universe, a gravitational ridge along which galaxies naturally flow. During the 1980s, cosmologists were just beginning to understand that galaxies aren't scattered randomly throughout space, but instead are organized into an immense cosmic web made up of filaments, walls, and voids spanning hundreds of millions of light-years. In this model, the Great Attractor might not be a single object at all, but rather a gravitational focal point where several of these vast cosmic objects' filaments intersect, a kind of supercluster junction in the architecture of the cosmos. For a time, some even speculated whether the Great Attractor could be a region of space with exotic properties, perhaps involving massive black holes or unknown physical phenomena. A few fringe theories, popularized in the media, suggested that it might represent a gravitational anomaly, unlike anything seen before, possibly even connected to regions of space-time beyond our observable universe. These ideas, though largely dismissed by mainstream science, reflected the sense of awe and confusion surrounding the phenomenon. As more data accumulated, however, the focus returned to more grounded, though no less fascinating possibilities. Astronomers suspected that the Great Attractor's gravitational influence might be distributed over a very large volume of space, composed not just of one cluster, but of multiple massive clusters and superclusters, each adding to the overall pull. But because this region lies behind the dense plane of the Milky Way, direct observation remained frustratingly difficult. The hypothesis of a massive obscured supercluster became the most compelling explanation, awaiting confirmation from non-visible wavelengths that could peer through the galactic dust. By the late 1980s, astronomers began using infrared and radio observations to look beyond the optical barrier. These alternative wavelengths revealed faint traces of galaxies that had been hidden from view. And indeed, there appeared to be hints of a massive cluster lying in the very heart of the Great Attractor's suspected location. This was a breakthrough that began to transform early speculation into a more concrete picture. The gravitational anomaly wasn't an illusion, nor was it a single exotic object. It was a massive, sprawling structure of galaxies and dark matter, buried deep behind the Milky Way's disk. Even as the early hypotheses evolved, the mystery of the Great Attractor served as a catalyst for one of the most significant shifts in cosmology, the realization that the universe is far more structured, interconnected, and dynamic than once believed. The early debates about its nature paved the way for the eventual discovery of other vast cosmic entities, such as the Norma cluster and the Shapley Supercluster, which would later reveal that the Great Attractor might not even be the final destination of our galactic motion, but just one gravitational waypoint in a much larger flow through the universe. The early theories about the Great Attractor, though sometimes speculative, captured the essence of what makes astronomy so powerful: the ability to infer the existence of something enormous and unseen purely through the evidence of its influence. Long before we could see what lay behind the Milky Way's veil, astronomers had already mapped its gravity, like cartographers charting the depths of an unseen ocean by studying the waves on its surface. And soon, that invisible mass would begin to reveal itself in clearer form, not through optical telescopes, but through the eyes of instruments capable of seeing the universe in a completely different light. Buried deep in the zone of avoidance, scientists would discover a colossal structure that could finally account for much of the Great Attractor's mysterious gravitational force, the Norma cluster. By the late 1980s and early 1990s, as astronomers relentlessly pursued the mystery of the Great Attractor, new technology began to peel back the cosmic curtain that had long concealed it. Visible light telescopes had failed. The Milky Way's thick veil of dust and gas was simply too dense. But when scientists turned to radio, infrared, and especially X-ray observations, an astonishing revelation began to emerge from behind the zone of avoidance. At the precise region where the gravitational pull was strongest, deep within the constellation Norma, they discovered a colossal concentration of galaxies. This immense, hidden structure would come to be known as the Norma cluster, and it quickly became the most promising candidate for the core of the Great Attractor. The discovery was monumental because it provided the first tangible evidence of something massive enough to explain at least part of the mysterious gravitational draw. Using radio telescopes, astronomers were able to detect emissions from hydrogen gas in galaxies that lay far beyond the Milky Way's dusty barrier. These radio signals travel effortlessly through interstellar dust, allowing scientists to chart galaxy distributions that had been invisible to optical instruments. At the same time, infrared telescopes such as those aboard the Infrared Astronomical Satellite (IRAS) began mapping heat signatures from galaxies hidden behind the Milky Way's plane, revealing an enormous congregation of galactic systems clustered together at roughly 200 million light-years away. But the real breakthrough came with X-ray astronomy. Galaxy clusters are not only collections of galaxies, they are also enormous reservoirs of superheated gas that emit strong X-rays. In the early 1990s, space-based observatories such as ROSAT, the Röntgen satellite, and later Chandra began detecting intense X-ray emissions from the Norma region, emissions that could only come from a structure of tremendous mass. This X-ray glow confirmed that the Norma cluster, also known as Abell 3627, was indeed a massive galaxy cluster, one of the largest concentrations of matter known in the nearby universe. The Norma cluster is truly colossal. It contains thousands of galaxies, each with hundreds of billions of stars, along with vast amounts of dark matter and superheated gas. The total mass of the cluster is estimated to be on the order of 10 to the 15th solar masses, roughly a quadrillion times the mass of our Sun. To put that into perspective, it's comparable in mass to the Coma cluster, one of the most massive and well-studied clusters in the observable universe. And, significantly, its location aligns almost perfectly with the suspected coordinates of the Great Attractor's gravitational center. What made the discovery even more exciting was the realization that the Norma cluster wasn't just an isolated feature. It appeared to sit at the crossroads of several cosmic filaments. These filaments are the enormous, thread-like structures that make up the universe's large-scale architecture, connecting clusters and superclusters across hundreds of millions of light-years. The Norma cluster, then, might not just be a single gravitational anchor. It could be part of a much larger structure, a kind of cosmic junction where matter from multiple filaments converges. As scientists studied the cluster more closely, they found galaxies in various stages of interaction, merging, colliding, and distorting one another under immense gravitational stress. Such activity is typical in regions of intense mass concentration, where galaxies fall inward under their mutual attraction, heating the intergalactic gas and generating the powerful X-rays that first revealed Norma's existence. These violent cosmic collisions are a telltale sign of a dense gravitational environment, exactly the kind of setting that could produce the large-scale galaxy motions attributed to the Great Attractor. With the Norma cluster identified, astronomers finally had a concrete explanation, at least partial, for the mysterious flow of galaxies in our local universe. The gravitational influence of such a massive structure could easily account for the hundreds of kilometers per second of peculiar motion observed in the Milky Way, the Virgo cluster, and neighboring galaxies. It was as though a key piece of the cosmic puzzle had finally been uncovered from beneath the Milky Way's blinding glare. However, as often happens in astronomy, solving one mystery led to another. While the Norma cluster's mass was indeed enormous, calculations suggested that it alone could not fully account for the observed velocities. The gravitational influence seemed to extend even farther, implying that additional massive structures might lie beyond Norma, perhaps another, even larger concentration of matter pulling on everything in its vicinity. In other words, the Norma cluster was a major player in the Great Attractor's gravitational field, but it might not be the whole story. This realization spurred astronomers to look even deeper into that region of the universe, using ever more powerful instruments and longer wavelengths. As they mapped the cosmic flows in greater detail, they discovered that the Great Attractor appeared to be part of a much larger gravitational landscape, a sprawling superstructure stretching hundreds of millions of light-years beyond Norma. Yet, the Norma cluster remains a cornerstone in our understanding of the Great Attractor. It's the first solid evidence of the massive concentrations of matter hidden behind the Milky Way's disk, a testament to how modern astronomy can reveal the unseen through wavelengths invisible to the human eye. Its discovery was a triumph of persistence, ingenuity, and technology, a moment when the invisible became visible, and a key piece of one of the universe's greatest puzzles finally fell into place. Still, the question lingered. If the Norma cluster is only part of the story, what lies beyond it? Could the true gravitational heart of our region of the cosmos be even larger, more massive, and more mysterious than we imagined? The answer, as later research would show, would take the mystery of the Great Attractor to an entirely new scale, one that could only be explained by invoking the invisible scaffolding that holds the universe together: dark matter. The discovery of the Norma cluster was a milestone, a moment when the invisible began to take shape. But it didn't solve the entire puzzle of the Great Attractor. In fact, it raised an even deeper question. If the galaxies we can see don't account for all the gravity we feel, then what does? The answer, astronomers came to realize, lies in one of the most elusive and profound components of our universe: dark matter. Dark matter is one of the great enigmas of modern cosmology. Though it cannot be seen, touched, or detected directly through any known form of electromagnetic radiation, its gravitational influence is undeniable. Galaxies rotate faster than their visible mass allows. Galaxy clusters hold together despite their apparent lack of sufficient matter. And on the larger scales, the cosmic web itself, that vast, filamentary structure connecting all galaxies and clusters, is sculpted by the invisible scaffolding of dark matter. It is the unseen architecture of the cosmos. When astronomers began studying the Great Attractor in more detail, it quickly became apparent that the visible matter, the stars, galaxies, and glowing X-ray gas, simply wasn't enough to produce the gravitational force responsible for pulling entire clusters across hundreds of millions of light years. The calculations didn't add up. To create such a vast and coherent motion, there had to be far more mass in that region than what telescopes could observe. The most plausible explanation: the Great Attractor is not just made of galaxies and gas, but also of dense concentrations of dark matter whose gravity dominates the region. To understand why dark matter is so crucial here, we must consider how it shapes the universe. While ordinary visible matter, what scientists call baryonic matter, makes up only about 5% of the total mass energy of the cosmos, dark matter accounts for roughly 27%. The rest, about 68%, is dark energy, a mysterious force driving the universe's accelerated expansion. This means that most of the matter in the universe is invisible to us. The galaxies we can see are like tiny lanterns strung along an unseen framework, the dark matter halos and filaments that form the true structure of the cosmos. These dark matter concentrations act like cosmic magnets, their gravity pulling visible matter, gas, dust, and stars into clusters and superclusters. Over billions of years, they create deep gravitational wells into which galaxies fall, forming the great filaments and nodes of the cosmic web. The Great Attractor, then, is likely one of these gravitational wells, an enormous dark matter overdensity, a region where invisible mass is densely packed, exerting a pull so vast that it influences the motion of galaxies across hundreds of millions of light years. Evidence supporting this idea comes not only from velocity measurements, but also from computer simulations of large-scale cosmic structure formation. These simulations, which model the evolution of the universe using the laws of gravity and the properties of dark matter, show that galaxy flows like those observed around the Great Attractor naturally arise near dense dark matter concentrations. In these regions, galaxies don't just move randomly, they stream toward the centers of gravity defined by dark matter. This aligns perfectly with what astronomers observe in the direction of the Great Attractor: a coherent flow of galaxies converging toward a hidden mass concentration. Dark matter's role becomes even clearer when scientists consider the scale of the gravitational influence involved. The Milky Way and its neighboring galaxies are moving at speeds of around 600 kilometers per second, pulled by something located more than 200 million light-years away. For a force that strong to exist across such distances, the source must have a total mass equivalent to tens of thousands of Milky Ways, and most of that mass must be invisible. Visible galaxies, as massive as they are, simply don't account for that. Another clue comes from gravitational lensing, the phenomenon where massive objects warp the fabric of space-time, bending the light from more distant objects behind them. In regions near the Great Attractor, observations show subtle distortions in background light, consistent with the presence of large quantities of unseen matter. Though the data is difficult to interpret due to the obscuring effects of the Milky Way's disk, these gravitational hints strengthen the case that dark matter is a dominant player in this cosmic drama. It's important to note that dark matter isn't some exotic new force. It behaves just like ordinary matter under gravity. What makes it mysterious is that it doesn't interact with light or any form of electromagnetic radiation. It neither emits nor absorbs light, making it invisible across all wavelengths: radio, infrared, visible, X-ray, or gamma ray. We can only detect it through its gravitational effects, the way it shapes galaxies, bends light, and orchestrates the cosmic flow of matter. In the context of the Great Attractor, dark matter provides the missing piece of the puzzle. The galaxies we observe, including those in the Norma cluster, are likely embedded within a much larger, invisible dark matter halo. This halo forms the backbone of the gravitational well pulling on our galaxy and thousands of others. It's as if the Great Attractor is the visible tip of an iceberg, while the vast majority of its mass, the true engine of its gravitational might, lies hidden beneath the surface, unseen but profoundly felt. This revelation also connects the Great Attractor to the broader structure of the universe. Dark matter doesn't just exist in isolated pockets, it forms a continuous web connecting galaxy clusters and superclusters across billions of light-years. This means that the Great Attractor may not be an isolated anomaly at all, but rather a node within a much larger dark matter network, part of a colossal superstructure that extends even farther into space. Later discoveries, such as the identification of the Laniakea Supercluster, would confirm that the Great Attractor is one of the deepest gravitational basins within this immense web of dark matter and galaxies. Ultimately, dark matter reshapes how we perceive the mystery of the Great Attractor. It reminds us that what we see, the luminous galaxies, the glowing X-ray gas, the radiant stars, represents only a fraction of reality. The universe we inhabit is, in truth, mostly invisible, its shape and motion governed by forces that lie beyond our direct perception. The Great Attractor, then, isn't just a gravitational anomaly. It's a window into the dark heart of the cosmos, where unseen matter sculpts the destiny of entire galaxies. And yet, as astronomers traced the flow of galaxies beyond the Great Attractor, they began to realize that this dark, massive region might not even be the end of the gravitational story. Beyond it lies an even larger and more powerful structure, a supercluster so massive it may overshadow even the Great Attractor itself, tying our entire galactic neighborhood into one vast cosmic system, the Laniakea Supercluster. As the mystery of the Great Attractor deepened, astronomers began to ask a daring question. What if this colossal gravitational anomaly wasn't an isolated phenomenon at all? What if the Great Attractor was merely one part of a much larger, interconnected structure, a vast web of galaxies and dark matter spanning hundreds of millions of light-years? Over time, as observational data became more detailed, and as our understanding of cosmic flows improved, this idea began to solidify into something extraordinary. The Great Attractor, it seemed, was not a standalone feature, but rather a gravitational node, a deep valley within a cosmic basin far larger than anyone had imagined. And that basin turned out to be the heart of a truly immense structure, the Laniakea Supercluster, a galactic realm so vast that it redefined our sense of place in the universe. For decades, astronomers had known that the Milky Way wasn't alone, even on the grandest scales. Our galaxy belongs to the local group, a small collection of about 50 galaxies, including Andromeda and the Triangulum Galaxy, bound together by gravity. This local group, in turn, sits on the edge of a much larger structure, the Virgo Supercluster, a sprawling complex of thousands of galaxies spread across roughly 110 million light-years. For much of the 20th century, scientists assumed that the Virgo Supercluster was the primary large-scale structure to which our galaxy belonged. But the discovery of the Great Attractor challenged that assumption. If our galaxy, and indeed the entire Virgo Supercluster, was moving toward something beyond it, toward the Great Attractor region near Norma, then perhaps Virgo wasn't the full story. Perhaps it was just one tributary in a much larger cosmic river, all flowing toward a greater gravitational center. This insight forced astronomers to reconsider how they mapped the large-scale structure of the universe. In 2014, a breakthrough came that would transform our understanding of these enormous cosmic connections. Using data from the Cosmic Flows 2 project, a team of astronomers led by Brent Tully at the University of Hawaii created the most detailed map ever of galaxy motions in our local universe. By measuring not just where galaxies were located, but how they were moving relative to one another, the team could trace the gravitational landscape, the invisible valleys and ridges sculpted by mass and motion on intergalactic scales. What they found was breathtaking. Galaxies, it turned out, are not scattered randomly through space, nor do they move in isolation. They flow along vast gravitational currents drawn toward regions of higher density, just like rivers flowing toward the lowest points in a landscape. When Tully and his team mapped these flows, they discovered that the Milky Way, the Virgo cluster, and countless other galaxies were all moving together within a gigantic gravitational basin encompassing over 100,000 galaxies. This basin was defined by the same flow that led toward the Great Attractor. The astronomers named this entire region Laniakea, a Hawaiian word meaning immense heaven, a fitting name for what is now recognized as our home supercluster. The scale of Laniakea is almost incomprehensible. It stretches over 520 million light-years across and contains a mass equivalent to about 100 quadrillion suns. The Milky Way, our home galaxy, occupies a small corner of this vast realm, residing on one of its outer filaments like a single drop of water on the edge of a cosmic ocean. Within this supercluster, galaxies and clusters are not static. They are moving, flowing inward toward the center of gravity that defines the region. And that center, astronomers realized, coincides with the location of the Great Attractor. In other words, the Great Attractor is not an isolated gravitational oddity. It is the core of the Laniakea Supercluster, the deepest part of the gravitational well that holds our entire region of the universe together. The motion of our galaxy, the pull on the Virgo cluster, the drift of the Hydra Centaurus region, all are part of a single coherent flow within Laniakea's immense structure. What once appeared as a localized gravitational anomaly turned out to be the signature of a much grander architecture. This discovery marked a turning point in cosmology. It redefined our galactic address in the universe. For the first time, we could see not just where the Milky Way is, but where it belongs. We are part of Laniakea, a vast, interconnected realm of galaxies, clusters, and dark matter, all bound by gravity and moving together toward a shared gravitational center. It's a reminder that even our seemingly immense galaxy is just one tiny participant in a cosmic ballet on a scale almost beyond imagination. The visualization of Laniakea was equally stunning. When scientists plotted the flow lines of galaxies within this supercluster, they resembled swirling rivers converging toward a massive basin, the Great Attractor, before branching outward again toward neighboring superclusters. It became clear that the universe is a cosmic web, not just of matter, but of motion, a dynamic system in which gravity sculpts both the structure of space and the pathways of everything within it. Laniakea's discovery also provided an elegant solution to a long-standing puzzle. It explained why our galaxy is moving in the direction it is, at the speed it is, and why that motion doesn't stop with the Great Attractor. Even as we fall toward the Great Attractor's center, the entire region itself is being tugged by something even larger beyond it, the Shapley Supercluster, an enormous mass concentration lying farther in the same direction. This means that the Great Attractor is not the final destination of our cosmic journey, but rather one gravitational waypoint in a much larger, interconnected flow across the universe. By connecting the Great Attractor to Laniakea, astronomers unveiled a universe that is not only vast, but deeply interconnected. Each cluster, each filament, each galaxy is part of a vast gravitational ecosystem, a hierarchy of flows nested within even greater flows. The Great Attractor is a part of this cosmic symphony, its gravity shaping the motion of galaxies across hundreds of millions of light years, yet itself responding to even larger structures beyond. In a way, the realization that the Great Attractor is part of Laniakea gives the mystery a new kind of poetry. What once seemed like an invisible monster lurking in the dark has revealed itself to be the beating heart of an immense and elegant cosmic structure, the gravitational center of our galactic continent in the universe. It shows us that, even in the face of the unknown, there is order in the cosmos, a delicate, interconnected flow of galaxies and matter guided by gravity's invisible hand. And yet, even as we map the contours of Laniakea, questions remain. How deep does this structure go? How does dark matter weave its filaments through it? And beyond Laniakea, what greater gravitational influences still await discovery? To answer those, astronomers would have to expand their gaze even farther, to uncover what lies beyond the Great Attractor's reach, in the direction of an even more massive gravitational titan, the Shapley Supercluster. The word Laniakea, meaning immense heaven in Hawaiian, perfectly captures both the beauty and the incomprehensible scale of the supercluster we call home. Before 2014, our cosmic address was uncertain beyond the level of the Virgo Supercluster, a collection of thousands of galaxies, including the Milky Way. But new mapping techniques transformed our view of the universe. Astronomers realized that Virgo itself wasn't the whole story. It was merely one branch of a much larger gravitational domain. Through the work of Brent Tully and his colleagues, our place in the cosmos was redefined. We now belong to an enormous galactic structure stretching over 520 million light-years across and containing roughly 100,000 galaxies, the Laniakea Supercluster. The mapping of Laniakea was made possible through an extraordinary project called Cosmic Flows 2, which compiled precise measurements of the distances and velocities of thousands of galaxies. Unlike traditional maps that show only where galaxies are, these maps revealed how galaxies move, how they flow through the universe under the influence of gravity. Using this data, Tully's team didn't just chart static positions, they reconstructed the cosmic currents of motion, tracing the way galaxies drift through space over billions of years. When the team visualized these flows, a striking pattern emerged. Galaxies were not moving randomly. Instead, they flowed in coherent streams, like water in an ocean, converging toward regions of high density and away from vast, empty cosmic voids. These gravitational basins, where the flow lines came together, defined the boundaries of superclusters, and our own flow lines, when traced backward, all converged toward a single, massive region centered near the Great Attractor. This convergence marked the core of Laniakea. Every galaxy within this supercluster, including the Milky Way, the Virgo cluster, the Hydra Centaurus region, and countless others, moves inward toward that same gravitational center. It was a unifying discovery. The Great Attractor wasn't a mysterious anomaly pulling us away from everything else. It was the heart of a vast, interconnected system binding together tens of thousands of galaxies in a single gravitational embrace. In this framework, Laniakea isn't defined by arbitrary boundaries in space, but by gravitational influence, by the paths that galaxies follow. Imagine space as a vast topographic map where gravity carves valleys and peaks. Galaxies move like rivers flowing downhill, following the contours of this invisible landscape. The deepest part of the basin, the gravitational center, corresponds to the region around the Great Attractor. Everything within Laniakea flows toward that central valley, while beyond its edges, galaxies begin to flow toward other attractors, defining neighboring superclusters. The Laniakea Supercluster dwarfs every human notion of scale. Its diameter spans over 520 million light-years, so large that light itself, traveling at 300,000 kilometers per second, would take over 500 million years to cross it. The entire structure contains a mass of roughly 10 to the 17th solar masses, 100 quadrillion times the mass of our Sun. To grasp the enormity of this, consider that the Milky Way, with its 200 billion stars, is merely a tiny speck within Laniakea's cosmic expanse, orbiting a center we cannot see, toward which we are all slowly but steadily drifting. What makes Laniakea particularly fascinating is how it revealed the interconnectedness of the universe. Before this discovery, astronomers often spoke of galaxy clusters and superclusters as somewhat separate islands of matter floating in the cosmic sea. But the cosmic flows data showed that these islands are actually part of a continuous web, bound together not by proximity alone, but by motion, by gravity, and by the invisible scaffolding of dark matter. The boundaries of superclusters are not physical walls, but gravitational watersheds, regions where the flow of galaxies diverges, much like the way rivers on Earth separate into distinct drainage basins depending on the slopes of the terrain. The visualization of Laniakea, created by Tully's team, was both scientifically profound and deeply poetic. Imagine countless golden points representing galaxies, connected by smooth streamlines showing their motion through space. These lines converge in swirling patterns toward the Great Attractor, the deepest part of the gravitational basin, then spread outward again toward adjacent structures. Surrounding Laniakea are other immense superclusters, such as Perseus Pisces, Coma, and Shapley, each forming part of a colossal tapestry that makes up the observable universe. In this vast gravitational landscape, the Great Attractor acts as the central hub of Laniakea's flow, the place where gravity reigns supreme. The Milky Way and our entire local group of galaxies are moving through this gravitational basin at about 600 kilometers per second, gradually spiraling inward, drawn by the combined mass of both visible and dark matter concentrated at its core. The discovery of Laniakea was more than just a new map. It was a revelation about how the universe works. It showed that our cosmic neighborhood isn't a static collection of galaxies, but a dynamic, interconnected flow system. It provided a tangible framework linking our motion, the motion of our galaxy cluster, and the mysterious pull of the Great Attractor. And it placed the Milky Way, and by extension humanity, within a grand cosmic structure that redefined our understanding of where we truly are in the universe. Perhaps most humbling of all, the identification of Laniakea underscored how small we are in the grand cosmic web. Our galaxy, which itself contains hundreds of billions of stars, is merely one of about 100,000 galaxies flowing through the Laniakea basin. Each of those galaxies holds countless worlds, stars, and possibly civilizations, all moving together toward a shared gravitational destiny. But as immense as Laniakea is, even it does not exist in isolation. Beyond its outer boundaries lie other superclusters connected through the same cosmic filaments of dark matter and gas. And one of those neighboring regions, the Shapley Supercluster, exerts such a powerful gravitational pull that it may be influencing even Laniakea itself, drawing it slowly across the cosmic web. The discovery of Laniakea answered one of astronomy's great mysteries, what the Great Attractor truly represents. But it also opened new questions about the deeper hierarchy of the universe. How far do these gravitational flows extend? Is there a structure larger than Laniakea? Does the universe contain an ultimate attractor, a final basin where all motion converges? These are questions that remain open, and they remind us that every time we think we've reached the edge of understanding, the cosmos stretches further still. And so, while the Great Attractor now has a home within the magnificent architecture of Laniakea, the flow of galaxies doesn't end there. Beyond its vast borders lies an even greater gravitational giant, one so massive that it might shape the motion of not only our supercluster but countless others. The Shapley Supercluster, the next step in our journey toward understanding the grand gravitational geography of the universe. The universe, despite its apparent stillness when viewed from our tiny vantage point on Earth, is in constant, graceful motion. Every galaxy, every cluster, every filament of cosmic matter is moving, not in chaotic, random directions, but in vast, coordinated streams shaped by the invisible hand of gravity. This grand motion is what astronomers call cosmic flow, and it reveals the universe as a living, dynamic system, one where galaxies drift through the fabric of space like rivers following the contours of an unseen landscape. To grasp the concept of cosmic flow, it helps to imagine the universe as a three-dimensional terrain made not of soil or rock, but of space-time itself, a surface warped and sculpted by the distribution of mass and energy. Where matter is dense, where galaxies, clusters, and especially dark matter accumulate, the terrain dips, forming gravitational wells. Galaxies, like water, naturally flow downhill along these slopes, moving towards the deepest valleys. The Great Attractor is one such valley, a gravitational basin where the density of matter is so high that it pulls galaxies from hundreds of millions of light years around it into a slow but steady inward drift. This motion is subtle on human timescales, but monumental over cosmic ones. The galaxies themselves aren't flying through space at random. They're moving as part of immense interconnected streams that trace the universe's cosmic web. These flows aren't governed by collisions or turbulence. They are the result of gravity sculpting the geometry of the cosmos over billions of years. Just as rivers carve valleys and follow the topography of Earth, galaxies follow the invisible gravitational contours created by the uneven distribution of matter, both visible and dark. The evidence for these flows became undeniable through the mapping of peculiar velocities, the deviations of galaxies' motion from the overall cosmic expansion. When astronomers charted these peculiar velocities, they found clear patterns. Galaxies were streaming along filamentary paths, converging toward massive attractors like the Great Attractor, and diverging away from vast, empty voids. These voids, enormous expanses nearly devoid of galaxies, act like the highlands between gravitational valleys, pushing matter outward as the denser regions pull it in. In this sense, the universe behaves less like a static explosion of matter and more like a vast, fluid system. Gravity acts as the flow's guiding force, drawing galaxies into regions of high density, while dark energy, the mysterious force driving cosmic expansion, acts in the opposite direction, stretching space and separating structures on the largest scales. The interplay between these two forces gives the universe its shape, texture, and motion. The Great Attractor represents one of the more striking local examples of this gravitational dominance, a place where the pull of matter temporarily overpowers the expansion of space, bending the flow of galaxies around it like a whirlpool in a cosmic current. It's important to realize that this flow isn't just an illusion caused by our motion. When scientists measure the peculiar velocities of thousands of galaxies, the same pattern appears from every perspective. Galaxies all around us, not just those near the Milky Way, are moving toward the same general region. This coherence indicates that the Great Attractor's gravitational basin truly exists, and that it defines a local flow field within the larger structure of the Laniakea Supercluster. Within this field, galaxies don't move independently. Their trajectories are interwoven, each responding to the same gravitational gradient that channels their motion inward. The beauty of cosmic flow lies in its elegance and order. The universe, which might seem chaotic at first glance, reveals itself to be astonishingly organized. On the largest scales, galaxies form a cosmic web, an intricate network of filaments and nodes where matter congregates at intersections and thins out in between. Cosmic flows trace these filaments perfectly. They reveal that galaxies move along the very same structures that define the universe's architecture, flowing toward dense clusters and superclusters like droplets traveling down an invisible slope toward the ocean. The Great Attractor, buried deep in the fabric of the Laniakea Supercluster, is one of the lowest points in this gravitational landscape, a place where many of these cosmic rivers converge. In many ways, cosmic flow redefines how we think about motion in the universe. On human scales, motion feels absolute. We walk, we drive, we orbit. But on cosmic scales, motion becomes relative and collective. The Milky Way isn't simply moving through space. It's being carried along by a much larger gravitational current that also includes the Virgo cluster, the Hydra Centaurus region, and tens of thousands of other galaxies. It's as though we're all aboard a massive galactic raft, drifting slowly but irresistibly down a river carved into the fabric of space-time itself. When visualized, these cosmic flows form breathtaking patterns. Imagine countless arrows representing the directions and speeds of galaxies, all curving and converging toward massive gravitational centers. Near the Great Attractor, the arrows tighten and swirl inward, showing galaxies falling toward the gravitational basin. Around the edges of voids, the arrows curve outward, showing galaxies being gently pushed away. It's a delicate, ever-changing balance between attraction and expansion, between gravity's pull and the universe's outward stretch. And yet, even as galaxies move toward the Great Attractor, they are not fated to collide in any catastrophic sense. The expansion of space ensures that, on the largest scales, the universe continues to stretch faster than local gravity can overcome it. The galaxies' paths are subtly curved, not plunging directly inward, but following the smooth contours of the gravitational field, like leaves floating in a slow, spiraling eddy. This is what makes the phenomenon so fascinating. Cosmic flow is not a violent rush, but an ancient, steady drift that has been unfolding for billions of years and will continue for billions more. The study of cosmic flow has become one of the most powerful tools for mapping the invisible mass of the universe. By tracking how galaxies move, astronomers can infer the distribution of both visible matter and dark matter, revealing the hidden structure that shapes everything. Through these maps, the Great Attractor stands out, not as an isolated monster, but as one node in a vast and continuous network of motion, one gravitational basin among many in the grand topography of the cosmos. Ultimately, cosmic flow reminds us that we are part of something far larger than we can see. Our galaxy is not stationary. It is one traveler among billions, drifting through a vast, interconnected ocean of gravity. The Great Attractor, immense and unseen, is simply one of the many destinations along that flow, a deep eddy in the infinite current of the universe, guiding galaxies across unimaginable distances in a cosmic journey that will never truly end. Beyond the mysterious gravitational basin of the Great Attractor, where the galaxies of the Laniakea Supercluster converge, lies an even greater cosmic colossus, a structure so vast and massive that it may overshadow the Great Attractor itself. This immense region, located farther along the same line of motion, is known as the Shapley Supercluster, and it stands as one of the most massive concentrations of galaxies in the observable universe. For many astronomers, it represents the next great chapter in our understanding of cosmic motion, a discovery that suggests the Great Attractor may not be the ultimate gravitational destination of our galaxy's journey, but merely a stepping stone on the way towards something far larger and more powerful. The Shapley Supercluster, also called the Shapley concentration, lies roughly 650 million light-years away in the direction of the constellation Centaurus, not far on the sky from the Great Attractor's coordinates. First identified in the 1930s by American astronomer Harlow Shapley, it remained largely theoretical for decades, as early telescopes couldn't resolve its full scale. But as observational astronomy advanced, especially in radio and X-ray wavelengths, the true immensity of this structure came into focus. What astronomers found was staggering. The Shapley Supercluster contains more than 8,000 galaxies, organized into at least 25 major galaxy clusters, including the massive Abell 3558 cluster at its heart. The total mass of the Shapley Supercluster is estimated to be over 10 to the 17th solar masses, roughly 10 million billion times the mass of our Sun. To put that in perspective, it's thought to be at least 10 times more massive than the Great Attractor region, a cosmic giant whose gravitational pull reaches across hundreds of millions of light-years. It is in fact so massive that it may be the largest gravitational structure in our local region of the universe, capable of influencing the motion of superclusters far beyond Laniakea's boundaries. As astronomers refined their maps of cosmic flows using data from the Cosmic Flows 2 and later Cosmic Flows 3 projects, a fascinating picture began to emerge. The direction of our galaxy's motion, along with that of the Virgo and Hydra Centaurus clusters, seemed to point not just toward the Great Attractor, but beyond it, straight toward the Shapley Supercluster. This observation led many researchers to propose that the Great Attractor might not be a gravitational endpoint at all, but rather an intermediate node, a way station along a deeper gravitational gradient that extends all the way to Shapley. If the Great Attractor is a basin, then the Shapley Supercluster is the continental lowland, a deeper, broader gravitational valley into which galaxies from enormous distances are slowly flowing. The galaxies around us, including those in Laniakea, may therefore be influenced by both structures simultaneously: the closer, local pull of the Great Attractor and the more distant, overwhelming draw of the Shapley Supercluster. These two forces together shape the peculiar velocities we observe, the subtle deviations in motion that give astronomers clues about the invisible topography of gravity in our universe. To visualize this relationship, imagine a cosmic landscape shaped by gravity rather than geography. The Great Attractor is a massive hill that dips downward, pulling galaxies toward it. But beyond it, the terrain descends even more steeply toward Shapley, whose gravitational potential well is deeper and broader. Galaxies like our own are therefore not just falling into one valley, but moving along a long, interconnected slope, drawn by the combined gravitational influence of both structures. This concept helps explain why the flow of galaxies in our region doesn't stop at the Great Attractor, but continues toward Shapley, as though the universe itself were gently cascading down an invisible gravitational slope. Observations in multiple wavelengths, from infrared to X-ray, have revealed the Shapley Supercluster to be extraordinarily rich in hot, intergalactic gas and massive dark matter halos. The intense X-ray radiation emitted from its central galaxy clusters indicates vast amounts of high-energy plasma, heated to tens of millions of degrees by the gravitational compression of matter. These observations confirm that Shapley is not just large in size, but also immensely dense, a true gravitational powerhouse in the local cosmos. Recent computer simulations of cosmic structure formation have also shed light on the possible connection between the Great Attractor and the Shapley Supercluster. In these simulations, galaxies and clusters flow along cosmic filaments, enormous tendrils of dark matter that weave throughout the universe. The Great Attractor appears to be located at the intersection of several such filaments within the Laniakea Supercluster, while the Shapley Supercluster lies farther along the same filamentary pathway. This suggests that the two are part of the same cosmic river system, connected by dark matter streams that channel the motion of galaxies over hundreds of millions of light years. In this context, the Great Attractor and the Shapley Supercluster are not competing gravitational forces, but complementary ones, sequential structures within the same cosmic flow. The Great Attractor represents a local convergence zone where galaxies are currently being drawn inward, while the Shapley Supercluster acts as the deeper, more distant gravitational basin guiding the ultimate flow of this entire region of the universe. This dual attraction could explain why the Milky Way and its neighboring galaxies are moving so rapidly, around 600 kilometers per second relative to the cosmic microwave background, and why this motion continues in a direction that aligns so well with both structures. The realization that the Shapley Supercluster might dominate our region's gravitational dynamics was a humbling revelation. It expanded our cosmic horizon once again, showing that even the immense Great Attractor, which once seemed so unique and powerful, is just one feature within a far greater cosmic landscape. The hierarchy of structure in the universe, galaxies, clusters, superclusters, and beyond, seems to stretch endlessly, each layer embedded within an even larger web of mass and motion. And yet, what makes this even more fascinating is that all of it, from the Great Attractor to Shapley and beyond, exists within a universe that is still expanding. These enormous gravitational flows take place against the backdrop of cosmic expansion, meaning that while space itself stretches, gravity continues to knit matter into coherent, dynamic structures. The Shapley Supercluster, in this sense, represents not a contradiction to cosmic expansion, but a localized victory of gravity over the stretching of space, a region where matter has gathered and continues to gather, forming one of the deepest wells in the cosmic landscape. The discovery of Shapley's role in our motion adds a new layer of depth to the Great Attractor mystery. It reminds us that the universe is not static or hierarchical in any simple way. It's an intricate system of interlocking gravitational influences, where every attractor, no matter how immense, is itself part of a larger gravitational pattern. The Great Attractor may have captured our attention first, but it is the Shapley Supercluster that likely rules the broader flow of our cosmic neighborhood, a true gravitational titan, shaping the destiny of galaxies across hundreds of millions of light years. And yet, even as astronomers uncover the immense scales of these structures, they must still contend with the many misconceptions that surround them, especially the idea that galaxies are falling into these attractors in a straightforward sense. The truth, as always, is far more nuanced, involving the delicate balance between gravity's pull and the universe's relentless expansion. One of the most common misconceptions about the Great Attractor, and indeed about cosmic motion in general, is the idea that galaxies are literally falling into it, as if into a giant cosmic sinkhole or black hole. It's a vivid image and an easy one to imagine. Entire galaxies spiraling inward, accelerating towards some massive center until they vanish into oblivion. But this is not what's happening. The reality is both more subtle and far more fascinating. Galaxies are not plunging into the Great Attractor in a catastrophic freefall. Rather, they are drifting within a complex interplay of forces, guided by gravity, but also carried by the ongoing expansion of the universe. To understand this properly, we need to recall one of the most fundamental principles in modern cosmology. The universe is expanding. Ever since the Big Bang, roughly 13.8 billion years ago, space itself has been stretching, carrying galaxies along with it. This expansion isn't like an explosion of matter into empty space. It's the expansion of space itself. The distances between galaxies grow over time, not because the galaxies are moving through space, but because the fabric of space-time between them is increasing. However, this expansion isn't uniform on all scales. On smaller, local scales, within galaxies, galaxy clusters, and even superclusters, gravity resists that expansion. The force of gravity pulls matter together, holding galaxies and clusters in place, while the rest of the universe continues to stretch. This creates a delicate balance. On large scales, the universe expands. On local scales, matter clumps together and resists being pulled apart. The motion of galaxies toward the Great Attractor occurs within this balance. So, rather than falling in a literal sense, galaxies are experiencing peculiar velocities, additional motions superimposed on the general expansion of the universe. Every galaxy, including our own Milky Way, participates in the cosmic expansion. The larger the distance between two galaxies, the faster they appear to move apart. Yet, local gravitational forces can slightly alter this motion. In the regions around the Great Attractor and the broader Laniakea Supercluster, the gravitational pull from the dense concentration of matter causes galaxies to deviate from the pure expansion flow, drawing them slightly inward. Think of it like this. Imagine you're floating on a river that flows smoothly downstream. That flow represents the overall expansion of the universe, everything moving apart. Now, imagine that the river's surface isn't perfectly uniform. There are gentle eddies and currents where the water flows a little differently, swirling around small depressions or obstacles beneath the surface. These eddies represent local gravitational effects, regions where gravity has carved out valleys in the cosmic landscape. The Great Attractor is one of those valleys. The galaxies drifting toward it aren't defying the river's flow. They're simply following a slightly different path along its contours. This is what astronomers mean when they say that galaxies are being drawn toward the Great Attractor. It's not a collision course or a plunge into a void. It's a gravitational drift, a subtle deviation from the background expansion caused by the uneven distribution of mass in the universe. The galaxies continue to move apart overall, but relative to one another, and especially relative to the cosmic microwave background, they show a collective motion toward the region of greatest gravitational influence. This concept often confuses people because we're used to thinking of gravity as something that causes direct, observable motion, like a falling apple or an orbiting planet. But on cosmic scales, gravity acts differently. It doesn't pull galaxies across space so much as it warps the fabric of space-time, creating regions where the flow of galaxies subtly converges. The galaxies themselves don't feel any local wind or sense of motion. Instead, the space they inhabit is curved in such a way that their natural trajectories, their geodesics, lead them toward regions of higher mass density. Crucially, even in regions like the Great Attractor, the overall expansion of the universe continues. On the larger scales, those exceeding the boundaries of superclusters, the stretching of space dominates completely. Galaxies separated by billions of light years are moving away from one another so rapidly that no gravitational pull could ever overcome that expansion. This is why, despite the immense gravity of the Great Attractor and the Shapley Supercluster, these structures remain local phenomena in the grand scheme of the cosmos. They influence the motions of galaxies in their vicinity, but cannot halt or reverse the universe's overall expansion. There's another layer of nuance here that makes the Great Attractor's influence even more fascinating. The galaxies within Laniakea, including our own Milky Way, are all participating in a collective flow toward the region of greatest density. However, this doesn't mean that galaxies are closing in on each other at an accelerating rate, or that they'll ever merge into a single point. Instead, the flow represents a state of dynamic equilibrium. Galaxies orbiting and drifting within the gravitational landscape of their supercluster while still being stretched apart by cosmic expansion. Over billions of years, these motions will evolve, but they won't lead to a cosmic collapse. In fact, because the universe's expansion is accelerating due to dark energy, the long-term future of these flows is one of gradual separation. While gravity still binds structures like galaxies and clusters together, dark energy ensures that space will continue to expand faster and faster on the largest scales. This means that the influence of structures like the Great Attractor and even the Shapley Supercluster will eventually diminish as galaxies outside their gravitational reach move away forever, carried by the inexorable tide of expansion. So, when we say that the Milky Way and other galaxies are moving toward the Great Attractor, we're describing a relative motion, not an inevitable collision. We are flowing along the contours of space-time, guided by gravity, even as the universe around us continues to stretch and evolve. It's a motion within motion, a graceful dance between attraction and expansion, where gravity pulls on the local scales even as the universe itself expands on the grandest ones. This distinction might seem subtle, but it's profoundly important. It transforms the Great Attractor from a threatening cosmic abyss into what it truly is, a gravitational hub in the grand cosmic web, shaping the paths of galaxies without consuming them. It's a testament to the harmony of the cosmos, an interplay of forces that create order, structure, and motion without chaos. And as we come to understand this balance more deeply, astronomers begin to wonder what the future holds. What will become of these cosmic flows as the universe ages? Will the galaxies of Laniakea continue their slow drift toward the Great Attractor indefinitely, or will dark energy eventually tear even superclusters apart? The answer lies in the evolving story of cosmic expansion, a story that continues to unfold as we peer further into the depths of time and space. When we gaze into the night sky, we are not looking at a static universe frozen in place. Every point of light, every star, every galaxy, every cluster is moving, evolving, and slowly reshaping the cosmic landscape over unimaginable spans of time. The Great Attractor, the Shapley Supercluster, and the vast network of gravitational flows that bind them are all part of this continuous motion. But what does the future of that motion look like? How will these immense gravitational structures shape the destiny of our local universe in the eons to come? Scientists believe that, over the next several billions of years, the galaxies within the Laniakea Supercluster, including the Milky Way, will continue their slow, graceful drift toward the gravitational center defined by the Great Attractor and the larger Shapley Supercluster beyond it. These flows are not violent or chaotic. They are the quiet, steady migration of galaxies across hundreds of millions of light years, guided by gravity's invisible hand. Yet even this grand movement will unfold against the backdrop of another, even more powerful cosmic process: the accelerating expansion of the universe driven by dark energy. In the near future, on cosmic timescales, meaning tens to hundreds of millions of years, the local universe will still look much as it does today. The Milky Way and the Andromeda Galaxy are expected to merge in about 4.5 billion years, forming a new elliptical galaxy, sometimes called Milkomeda. Together, this merged system and its satellite galaxies will orbit within the local group, which itself remains gravitationally bound despite the universe's expansion. Our local group will continue moving through space as part of the greater flow toward the Great Attractor, drawn along by the subtle but persistent gravitational tug of the dense matter lying in that direction. However, while gravity keeps galaxies within superclusters like Laniakea bound together, the accelerating expansion of the universe ensures that structures on larger scales, beyond superclusters, will drift ever farther apart. Over the next tens of billions of years, this cosmic tug-of-war between gravity and dark energy will profoundly reshape the universe's structure. The galaxies of Laniakea will continue their slow inward drift toward the Great Attractor's basin. But beyond its boundaries, space itself will stretch so rapidly that other superclusters will slip out of view entirely. The light from distant galaxies, already faint and redshifted by the universe's expansion, will become so stretched that it fades into invisibility. Eventually, the universe will reach an era in which gravitationally bound regions, superclusters like Laniakea, clusters like Virgo, and massive concentrations like the Great Attractor, will become cosmic islands, isolated from one another by ever-expanding oceans of dark energy-dominated space. The galaxies within each island will remain bound together, but everything beyond will recede faster than light, cut off from interaction forever. In this future, the Great Attractor and the Shapley Supercluster may serve as centers of gravity within their isolated regions, continuing to shape the orbits and flows of galaxies that remain gravitationally connected. Over the next 100 billion years or so, these local structures will gradually coalesce and settle. Galaxies will merge and grow more massive, forming giant elliptical galaxies and clusters surrounded by halos of dark matter and hot gas. The cosmic flows we observe today, those majestic streams of galaxies moving toward the Great Attractor, will slow as the gravitational wells fill and balance out. The overall architecture of our supercluster will reach a kind of dynamic equilibrium, where galaxies orbit within the deep gravitational valleys carved by dark matter and visible mass. In this far future universe, the grand cosmic web that we now see stretching across billions of light years will appear very different. The vast filaments connecting superclusters will thin and eventually snap as expansion pulls them apart. The universe will become a patchwork of isolated gravitational domains, each a self-contained realm of stars and galaxies. Our region, the Laniakea Supercluster, will remain intact, but beyond it, the cosmic horizon will fade into darkness. The Great Attractor, once just one gravitational feature among many, may become the dominant center of our entire visible cosmos. What's both humbling and awe-inspiring is that the process shaping this future is already underway. Even now, galaxies are slowly flowing along the cosmic filaments toward the gravitational wells of massive clusters and superclusters. Observations and simulations suggest that over the next few billion years, the Virgo cluster, the Norma cluster, and neighboring systems could gradually drift closer together, subtly reshaping the structure of Laniakea. It's not a collapse in the traditional sense. The universe's expansion prevents any large-scale implosion. but rather a slow gravitational tightening, a cosmic settling into balance. Eventually, the night sky itself will reflect these vast changes. As expansion accelerates and distant galaxies slip beyond our cosmic horizon, fewer and fewer galaxies will remain visible. The Great Attractor's gravitational influence will continue to act on the matter within its domain, but the broader cosmic dance will grow quieter. From the perspective of a future observer, billions of years from now, the universe may appear static and empty, a handful of galaxies orbiting one another in a sea of darkness. The knowledge that our galaxy is part of a grand cosmic flow toward the Great Attractor, part of a network of structures stretching across hundreds of millions of light years, may be lost to time, hidden by the universe's own expansion. Yet even as cosmic isolation deepens, the structures that remain, like Laniakea and the Great Attractor, will continue to bear silent witness to the history of the universe. Their shapes, motions, and gravitational fields are the fossilized imprints of billions of years of cosmic evolution, the end result of the same gravitational processes that began when the first matter clumped together after the Big Bang. In a sense, the Great Attractor is not only a destination, but a record, a gravitational archive of everything that has ever flowed toward it. From a philosophical perspective, the future of these cosmic flows reminds us of the fleeting nature of cosmic connectedness. Today, we can see galaxies billions of light years away, trace their motions, and map the intricate web that links them all. But in the deep future, as the expansion of the universe continues, that connection will fade. The galaxies of the Great Attractor and Shapley Supercluster will remain gravitationally entwined, but the greater universe beyond will slip away into eternal night. Still, the knowledge we have now, that our galaxy, our stars, and even our planet are part of this vast and flowing cosmic network, gives us a profound sense of place. We are not standing still. We are participants in a majestic drift through space-time, part of an ongoing story that spans billions of years. Our future, like our past, will be shaped by forces that are both incomprehensibly vast and exquisitely ordered, the quiet pull of gravity, the steady expansion of space, and the eternal balance between the two. And as we continue to study these flows, astronomers look toward the next frontier, peering even deeper into the regions obscured by our galaxy, mapping the faint traces of matter that might further illuminate our cosmic journey. Because even as we look to the future, the Great Attractor still holds mysteries yet to be fully uncovered. Mysteries that could reshape not just our understanding of where we are, but of where we are going. Even though we now understand that the Great Attractor is part of the immense Laniakea Supercluster, and that the even more massive Shapley Supercluster lies beyond it, the mystery of what exactly resides within this obscured region of space is far from solved. The story of the Great Attractor is still unfolding, and astronomers continue to push the boundaries of observation to uncover what lies hidden behind the Milky Way's thick veil of dust and stars. This ongoing research represents one of the most challenging yet rewarding endeavors in modern astronomy, mapping the invisible heart of our galactic neighborhood. The region of the sky where the Great Attractor resides remains one of the most difficult areas to study because of the zone of avoidance, the thick band of the Milky Way's disk that blocks our view of the cosmos beyond. For decades, this barrier prevented astronomers from seeing the galaxies and clusters that might account for the mysterious gravitational pull influencing our entire region of the universe. But with the advent of new telescopes, advanced sensors, and multi-wavelength observation techniques, the curtain is finally beginning to lift. One of the key breakthroughs has come from radio astronomy. Unlike visible light, radio waves can penetrate the dense interstellar dust that obscures the galactic plane. Using massive radio telescopes, such as the Parkes Observatory in Australia, the Mir KT array in South Africa, and the Australian Square Kilometre Array Pathfinder, ASKAP, astronomers have been able to detect the faint radio emissions from hydrogen gas in galaxies hidden behind the Milky Way. These emissions occur at a specific wavelength of 21 centimetres, which acts as a cosmic beacon, allowing scientists to locate and map galaxies that would otherwise remain invisible. Through such surveys, astronomers have discovered hundreds of previously unknown galaxies in the direction of the Great Attractor, each helping to fill in the gaps in our understanding of the mass distribution in that region. These galaxies, many of which belong to the Norma cluster and neighbouring structures, form part of the vast gravitational network responsible for the peculiar motion of our galaxy and others nearby. The HI zone of avoidance survey, conducted with the Parkes telescope, was one of the first to reveal these hidden galaxies, dramatically improving our picture of the Great Attractor's surroundings. But radio telescopes are only part of the story. The development of infrared astronomy has also revolutionized our ability to peer through the galactic veil. Infrared light, which has longer wavelengths than visible light, can pass through much of the dust that blocks optical observations. Space-based infrared observatories such as NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, WISE, have been instrumental in detecting the warm glow of distant galaxies hidden behind the Milky Way. More recently, the James Webb Space Telescope, JWST, with its powerful infrared vision, has begun providing unprecedented views of dusty and obscured regions, revealing galaxies that were invisible even to previous generations of instruments. Meanwhile, X-ray observatories such as Chandra, XMM Newton, and EROSITA have helped astronomers detect the hot, diffuse gas that fills galaxy clusters. Gas heated to millions of degrees as gravity pulls matter together. X-rays can't penetrate the densest parts of the Milky Way's disk, but they can reveal massive structures just beyond it. Observations in X-ray wavelengths have provided further confirmation of the Norma cluster's mass and extent, as well as hints of other, fainter clusters that may contribute to the Great Attractor's gravitational field. These multi-wavelength studies, combining radio, infrared, X-ray, and even gamma-ray data, have given rise to a new era of cosmic cartography. Using data from dozens of observatories around the world and in space, astronomers can now construct detailed 3D maps of the hidden universe. These maps don't just show where galaxies are located, they also reveal how those galaxies are moving and how much mass must be present to account for their motion. Every new discovery adds another piece to the intricate gravitational puzzle surrounding the Great Attractor. The continuing quest to uncover this hidden region has also inspired the development of next-generation observatories. The upcoming Square Kilometre Array, SKA, a vast network of radio antennas being built across South Africa and Australia, will be the largest and most sensitive radio telescope ever constructed. When fully operational, it will be capable of detecting faint hydrogen signals from galaxies billions of light-years away, providing astronomers with the clearest picture yet of the structures hidden behind our own galaxy. With its immense resolution and sensitivity, the SKA is expected to map millions of previously unseen galaxies, potentially revealing the full structure of the Great Attractor and its connection to even larger cosmic features. Similarly, future space missions such as ESA's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope will study the large-scale structure of the universe in unprecedented detail, mapping the distribution of dark matter and dark energy through gravitational lensing and galaxy clustering. These missions will help scientists better understand how the Great Attractor and other massive structures formed, and how their gravitational influence has shaped the motion of galaxies across the cosmic web. Astronomers are also using supercomputers and cosmological simulations to model the Great Attractor's region, combining observational data with theoretical physics to recreate the gravitational interactions that give rise to the observed flows of galaxies. These simulations allow researchers to test various scenarios, such as how different distributions of dark matter or dark energy might affect the motion of galaxies, and to predict how the structures we see today will evolve in the distant future. Every advance in technology brings us closer to fully understanding the Great Attractor, yet the mystery remains tantalizingly open. Even with today's most sophisticated instruments, the dense dust and bright starlight of the Milky Way continue to obscure parts of this region, leaving gaps in our knowledge. Astronomers often describe the challenge as trying to map a city while standing in the middle of a blinding sandstorm. The outlines can be seen, but the finer details are lost in the glare. Still, the progress is remarkable. In just a few decades, the Great Attractor has gone from being an invisible enigma to a well-defined gravitational basin, connected to both the Norma cluster and the broader Laniakea Supercluster. The ongoing work to study this region continues to deepen our understanding not just of one part of the cosmos, but of how the universe itself is structured and how matter, both visible and dark, organizes itself into the grand architecture of the cosmic web. Perhaps the most inspiring aspect of this continuing exploration is that it unites every wavelength of the electromagnetic spectrum and every major field of astrophysics toward a single goal: to see the unseen. The Great Attractor remains a symbol of both mystery and progress, a cosmic reminder that even in the age of advanced technology and powerful telescopes, there are still places in the universe we can barely glimpse. And yet, with every new observation, we inch closer to lifting the veil entirely, revealing the full beauty and complexity of the forces shaping our galactic home. But even as astronomers probe deeper into this hidden frontier, one truth remains: the Great Attractor still guards its ultimate secrets. For all our instruments and models, we do not yet know precisely what lies at the deepest heart of its gravitational pull. And in that lingering mystery lies something profoundly human: the reminder that the universe is not fully known, and perhaps never will be. Even after decades of research, the Great Attractor remains one of astronomy's most haunting enigmas. We know it's there. Its gravitational influence is undeniable, yet we still can't see it clearly or fully explain it. Despite powerful telescopes, detailed sky surveys, and advances in multi-wavelength astronomy, much of this region remains shrouded behind the Milky Way's blinding veil. What we've uncovered is only part of the story: a massive gravitational basin linked to the Norma cluster, embedded within the Laniakea Supercluster, and perhaps drawn further toward the colossal Shapley Supercluster beyond. But the precise nature of its composition, how much of it is dark matter, how it connects to the surrounding cosmic web, and what hidden structures may still lie within, continues to elude us. This uncertainty is humbling. It reminds us that even in an era when we can peer back to the dawn of the universe, vast regions of the cosmos remain unseen and unexplored. The Great Attractor stands as a symbol of that mystery, a gravitational ghost tugging on our galaxy yet veiled from our sight. It's a testament to both the limits of human knowledge and the endless capacity for discovery that defines science itself. For all we've learned, the universe still holds secrets deeper than our instruments can penetrate, whispering from beyond the stars that the quest for understanding is far from over. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.